Today our goal is to analyze graphs of logarithmic functions and describe their features. We're going to kick off with a do now, reviewing previous lesson. So our lesson today is on logarithm functions. Have a go at these questions now. All right, let's have a little review from the previous class. So question number 1. We've got log base 4 of 128 minus log base 4 of 8, using the quotient property of logarithms. We can rewrite this one as log base 4 of 128 over 8. So this is log base 4 of 16. So that is log base 4 of 4 squared. So we get 2 log 4 of 4, which, if you remember, the logarithm in any base of the base is equal to 1. Question 2. Rewrite in base 2 and simplify. We've got log 64. So because no base is shown, these are common logarithms. So they're in base 10. If we want to write this in base 2, we want log base 2 of 64 divided by log base 2 of 10. Now, log 2 of 64 is log 2 of 2 to the 6 over log 2 of 10. So that's going to be 6 over log 2 of 10. That's as simple as we can go. Question number 3, ln e to the 6 minus 2 ln e. This is 6 ln e minus 2 ln e, which is 4 ln e. The base is e, so the log in any base of the base is equal to 1. So this is 4. Let's just look at the goals for today on our to know list. So logarithmic function is a function of the form shown here, where it inherits the properties from the exponential function, and the base b has to be positive, and the base b cannot equal 1. Now, this represents the inverse of an exponential function and is defined for all positive arguments. That's what that's saying there. It's defined for positive arguments. Defined for positive arguments means this argument here has to be positive. X minus h has to be positive. Key information. This is an inverse relationship, so the property that logarithmic and exponential functions undo each other can generally be expressed in the definition of the logarithm shown here, which is when you convert between exponential form and logarithmic form, you're effectively making the inverse of the equation. Graphically, this is shown as a reflection in the line y equals x. So this is our key to know line here. So what we see here is exponential form rewritten into logarithmic form produces the inverse function. Because these two are inverses of each other, they're going to be plotted like the graph here. We're looking as a reflection in the line y equals x. What we see here is an example of f f inverse of f of x is equal to x, and this one is f of f inverse of x is equal to x. The basic definition of the inverse property. So interesting to know, I've shown an exponential function here in the base a. The parent function is going to go through 0, 1, 1, the base, 2, the base squared. So the inverse function here is written in the base a. This one always goes through 1, 0, regardless of the base. Remember that fact. And then it's going to go through the base, 1, and the base squared, 2. The vertical asymptote of the line is the line x equals h. So when sketching, start by sketching your vertical asymptote. So the graph with its transformations is shown. And this approaches but never reaches the vertical asymptote. This is caused by that domain restriction. X minus h has to be positive. So the coefficients a, h, and k. A is our vertical dilation, h is our horizontal translation, k is our vertical translation. A portion of the graph is shown here of the exponential function f of x equals 1/2 times 3 to the x. Find the inverse function and sketch it. So let's start off with f of x. F of x is equal to 1/2 times 3 to the x. So the domain is x is all real numbers. The range is going to come from the horizontal asymptote. So here we have a no vertical translation. So that means that the range is going to be y is greater than 0. So to find the inverse function, we switch the domain and range, and this gives us 1/2 times 3 to the y. This is the inverse relationship at this point. And rearrange to make y the subject, we get 2 to the x is equal to 3 to the y. Apply the definition of the logarithm. Apply this here and switch from exponential form to logarithmic form. Switching to logarithmic form, the base is 3. So this is going to give us log base 3 of 2 to the x is equal to y. So switching to logarithmic form gives us this one. We've got our inverse function now. So write it using inverse function notation. F inverse of x is equal to log base 3 of 2 to the x. Whenever you write an inverse function, always state the new domain. So the new domain is where x has to be greater than 0. It takes the properties of the range of the original function. So plotting the curve is going to be quite easy. We just take these x and y coordinates and reverse them. So 0, 5 is going to be 0.5, 0. 1, 1.5 is going to be 1.5, 1. This is going to be 1.5, sorry. This is going to go through here at 0.5, 0. It's going to go through here at 1.5, 1. and it's going to go through 4.5, comma 2. It's going to go through 4.5, comma 2. Our vertical asymptote is going to be here. This is the line x equals 0, or let me draw that the other side. X equals 0. So our curve is going to look like this. All right, have a go at solving this problem. Draw on your information from last class, have a go at solving it, pause the video now. Okay, so we're going to find the function shown here in the graph. It's an exponential function. We can see there's no vertical translation. So it's of the form y, let me write it as f. So it's of the form f of x is equal to a times b to the x. Let's take the x and y coordinates. It goes through 0, 1. It goes through 1, 2. We can see here that the proportionality factor there is multiplied by 2. This implies that the base is equal to 2. It goes through here at 1, 0. This implies that a is equal to 1. So the function is f of x is equal to 2 to the x. So f inverse of x is equal to log base 2 of x, where x is greater than 0. So using this, we can find what the value of f to the minus 1 of 32 is. Now, it's actually easier just to take the exponential function. We'll set that one equal to 32 and solve. So this is 2 to the 5 is equal to 2 to the x. X is equal to 5. So f inverse of 32 is equal to 5. Okay, I'll do this first one and then I've got one for you to do next. So we need to find the x-intercept. So we set the equation equal to 0, log base 2 x minus 3 plus 1. Let's move the 1 across to the other side. We get log base 2 x minus 3. And at this point, we can change to exponential form. At this point, change to exponential form. So the base is 2. That means 2 to the 1 is equal to x minus 3. Which means x is equal to 5. Describe the end behaviors. Well, I'll leave that one for a minute. It's probably easy once I sketch it. So I think the best thing to do is to start with the equation of the vertical asymptote. The vertical of the asymptote is always x equals h. So this means x is equal to 3. Let's draw that now on our graph. And label. Sketching. Graph is going to look like this, and it's going to go through here at 5, 0. So describe the end behaviors. The limit as x approaches 3 from the positive side of f is equal to negative infinity. The limit as x approaches infinity of f is equal to infinity. Describe the transformations. We have a horizontal and vertical dilations. So we have a horizontal translation right 3 units. We have a vertical translation up 1 unit. I've done everything? Yes. All right. Have a go at one of these for yourself. Pause the video. Let's have a look at our answers. So set this equal to 0. We get log base 3 of x plus 1 minus 2. So So 2 is equal to log base 3 of x plus 1, rearranged to exponential form, and we get 3 squared is equal to x plus 1. So 8 is equal to x. State the equation of the asymptote. We get x is equal to minus 1. Sketch. Our vertical asymptote. X equals negative 1. This one is going to go through 8, 0. Our end behaviors. The limit as x approaches negative 1 from the positive side of f of x is equal to negative infinity. Our right-hand end behavior is the limit as x approaches infinity of f of x is equal to infinity. Now I'm showing with the limit statements that you can either write f for the function or f of x showing it what domain it's on. Both work. Describe the transformations. We have a horizontal translation left 1 unit. And a vertical translation down 2 units. Okay, have a go at the exit ticket. Use your calculator for this one. Before I do this question, let me just jump back. I made a slight error back here on this one. Here at this point, I should have subtracted the -1 across. So this is -1. So this is x equals a half minus 3. Sorry, a half plus 3, which is 3.5. So this goes through 3.5, comma 0. Sorry, let me just pause on that one. Couple of little corrections there. Okay, Maria made a deposit in a bank account and left money untouched for several years. The table lists the account balance at the end of each year. Maria is interested in having a function that predicts the year based on the balance will exceed a certain value. Create a function and use it to predict the year the account balance will exceed 1400. So let's start off by finding the function in terms of an exponential. What we're having here is the base. So pull up our calculator. Pull up the calculator, and we have 1020 divided by 1000. Press Control Enter. 1.02. So the function would be y equals our initial value is 1000 times 1.02 to the x. We want an inverse function for that one. So our function is going to be f of x is equal to, let me just do a little bit more math. Y over 1000 is equal to 1.02 to the x. So we want to find convert to log form. That means x is equal to log base 1.02 of y over 1000. So the function that we want is log base 1.02 of x over 1000. Then we wish to find f of 1400, and this will predict the year in which the account balance will reach that. So on our graphing calculator, just going to add a page. Control add page, add a graph page. I want logarithm base 1.02, 1.02 of control divide x over 1000. we want to graphically show this. This here is going to go through over here. Let me just do the menu, window settings. Our X value needs to go over 1,000. So I'll put 1,500. We can see it going through over here. We want to find the year it gets up to when we put in 1,400. So let's use the function. We want to enter 1,400, and that will give us 17. So it'll take 17 years. Okay, that's it for today. Thank you.